In this video, we will start to discuss Chapter 3b, which is Chapter 3 in our main textbook for the course. It's called Three Faces of a Derivative. I actually claim that there's four: graphical, numerical, verbal, and analytical. So first of all, let's take a look at a motivating example of why would one even consider having to compute a derivative. So here are some of the graphs that describe home sale prices, household income, and home ownership rate in the United States of America between 1985 and 2015. So maybe just pause the video for a minute and stare at these graphs and think about how would you verbally describe them. What is similar about these graphs? What is different about these graphs? How would you describe the trends in these graphs? Could you say that they're all increasing? Are they increasing at the same rate? Is one increasing faster than the other? Is it increasing throughout the 30-year period that we're considering? Now, once you've actually formulated some thoughts and descriptions verbally, let's try to put some numbers to it. If I was trying to quantify it, if I'm an economist, for example, and I'm trying to really think of what are some of the numbers that I can use to describe these things, the first thing that I can do is actually compute the averages. The average for the home sale price, for instance, the average comes out to be $4,900, and of course the units are dollars because that was our rise, per year because that was our run. Now, this is what we can then tell our, let's say, customers about what were the trends in home sale prices over the last 30 years. The average suggests that they were increasing on average by $4,900 a year. Okay, if we do the same exact type of calculation for household income, we will see that the average household income was increasing by $1,001 per year on average over the 30-year period in consideration. And then if we do the same thing with the home ownership rate, we will actually find something slightly surprising. Here, the last data point actually happens to be below the initial one, so our average comes out to be negative 0.01% a year. So then if you were putting in a sentence, you would say that the home ownership rate was decreasing by approximately 0.01% a year. Now that we have computed these, let's discuss, do these really describe what was happening to each one of these measures throughout the 30 years? So the average prices were allegedly increasing on average by $4,900 a year. Does that describe this graph very well? Well, I mean, you can say that, sure, I guess we can see a generally increasing trend, but the average fails to describe a much higher increase in the mid-2010s, or O's, I guess, and it really fails to describe this dip that happened, right? So in terms of describing the graph, this one is okay. What about the average income? The average income actually does seem to be steadily increasing at a fairly similar pace. So this is pretty good. The average describes the actual graph fairly well. What about the home ownership rate? The average claims that it was decreasing on average by 0.01%. Well, the home ownership rate was kind of steady, and then we saw an increase and then a decrease. So this average is providing a really quite terrible description of what is going on, right? So this is really quite bad. And this is generally the problem with averages, is that if you take 2 points, the initial and the final, to be far apart, like 30 years, a lot could have happened in the 30 years, but you're only judging the situation on the 2 points that the average has in its computations. The derivative will allow you to shrink that period and really look at a much smaller portion of the function or its graph, so you will be able to much better and more precisely describe what's happening, because your window that you've zoomed into is going to be tiny. Okay, so thinking back in terms of derivative, essentially this is why it's a much better measure than an average could ever be. The derivatives are computed from averages, just averages over much, much smaller periods of time, so small that the period of time is actually going to zero. So these are the three descriptions of the derivative. The first one is what we call analytical or formulaic. The graphical description is that it's a slope of a tangent line at that point, because at that point your secant line becomes a tangent line. So this is the graphical description. A derivative is also instantaneous rate of change at that point, and this is going to be our verbal description. The fourth representation of face of a derivative, if you wish, is going to be numerical approximations of a derivative. So numerical estimation, let's call them. Okay, and so this, the reason the book doesn't quite mention it separately as a face is because really you can think of that as computing the limit, except for you're not letting the time window go to 0, but you rather actually have a very, very small window that you're computing it over. The window is very small, it's going towards 0, but it's not a limit as x goes to 0. Now, the key things about the derivative is it does change depending on the point at which you're computing it at. Of course it does, right? It's a slope of a tangent line at a specified point that for some reason is of interest to you. So depending on the point, the derivative will have a different value. Different point, different derivative. That means, though, that the derivative itself is a function. And it depends on the point we're computing it at. Okay, so let's take a quick look at the animation here. So remember how we actually computed the derivatives is that we set, let's say I would like to compute the derivative at the purple point here. What I really am doing is I am computing the average between the 2 points, the slope of a secant line, what we call it. And then because I would like to not have an average over a large period of time, let's say, I'm going to bring these 2 points closer together. So as I'm moving this point closer and closer to my purple point, you notice that the secant line becomes a tangent line, right? Another really important observation here is that, look, when my 2 points are apart, the line, the green line, doesn't really do a very good job at mimicking what the parabola between the 2 points really looks like. There's quite a bit of space between my green line right now and my red parabola. But the closer I get to my purple point, even already right here, you can see how the green line really mimics the behavior of the parabola really quite well. Look at this right here, right? They're really, really close together. And the closer I get, the more my line looks like my function. And this is key because this is another way to think about when is a function not differentiable. If a function is differentiable, it means that near the point where you're taking the derivative or trying to, you have to be able to construct a tangent line, but that also means that your function actually has to look like a line near that point of tangency, right? So if it doesn't look like a line, if you zoom in really closely, then it's not differentiable. So let's recall that it wasn't, for example, differentiable at a corner. Sure, no matter how much I zoom in into the corner, a corner will never look like a straight line, right? Same with jumps and asymptotes and whatnot. So here's another really good example of that. This is a sine function, a very wavy function, but it doesn't actually take very long, very much zooming in to see that it becomes a pretty straight looking line, right? This means, at least visually, this gives us a really good sense of the fact that the sine function is differentiable. Okay, going back to this, the one thing that we're going to do next is, because the derivative can be approximated even purely from the graph at any given point as a slope of a tangent line, we're actually going to try to graph a derivative function given the original function. So this graph is the graph of my function f. What I would like to produce below it is the graph of its derivative. Okay, so the first thing to note, this is quite a sort of cognitively heavy process because what we're really trying to graph are slopes of a function, but on a different graph, right? So here I am actually graphing slope values, even is probably a better description of that. Slope values are what is being graphed on the bottom graph. Okay, so what one would do, and again, this is just a graphing exercise, so I'm not going to come up with an exact graph of a derivative, but I'm going to come up with a pretty good sketch of it. So what I'm going to think about is, if I were to construct a tangent line here, what would approximately the slope of it be? So for example, this tangent line that I just drew, let me just draw it again. So this tangent line, let's say at this point, what is the slope of this line approximately from this graph? Well, a slope of any line is rise over run. So all I have to do is think, okay, well, I'm just going to eyeball the rise over run of this particular line. And the rise here is 3 and the run is 1. So that means that at this x value right here, which corresponds to an x value here, my function has the slope of a tangent line equal to 3, which means that my derivative value is 3, right? So let's say my slope is 3, so my derivative value at this x point is going to be 3. Okay? So I'm literally graphing a tangent line, estimating what the slope looks like, and then graphing that as the y coordinate of the point on my derivative graph. Okay, and we're just going to do a bunch more tangent lines and take a look at what that might look like. Now, before I start just drawing 5 more tangent lines, let's maybe take a look at our function here and think of what are some of the points where tangent lines have an easy to compute slope. So to me, 2 points stand out. A point here, because the tangent line is horizontal, which means that the slope is 0, and another point with the same type of property here, where again the tangent line is horizontal, which means that the slope of it is 0. So that means that on this x coordinate, my slope and therefore my derivative value is 0, which means that here is my point on the derivative graph. Similarly for here, that means that at this point, my derivative value is 0. Okay, what else can we do? So I would like to draw a couple more lines just to give me some idea of what the slopes look like, right? So let's say I would like to draw a tangent line here. So again, now that means that I will be drawing what the function's slope, a tangent line slope is at this value of x. Now I'm going to approximate the slope. So let's say rise over run. At this point looks like rise was 2 and run was about 2. So my derivative value at that point is 1. Okay? And again, let's draw a couple more just to give us some sense. It's not like I'm going to draw like a ton of tangent lines here. I can see that the tangent lines are going to be getting less and less steep as I move towards this point here. So that already means that I can probably connect this graph this way. As my tangent line slopes get more and more shallow, that means that my slopes are getting smaller and smaller in terms of y values on the derivative graph. Okay, let's draw another one, maybe let's say it's 0 here, right? So let's say my slopes look something like this. And again, just doing rise over run here, well, rise over run here, I can see that my rise is about 1 and my run is about 2, except for my rise is actually a drop, which means, and of course I can see that, right? The tangent line slope here is negative, so that means that at 0, my derivative value is about -0.5, right? So this is slope -0.5. Okay, and so on. So maybe take a minute and compute a couple of other points just to really get into the process of trying to draw a tangent line, estimate its slope from the graph, and then actually plot that point on the derivative graph. In the end, for our graph, we should get something that looks like this. Increasing function means slopes of tangent lines are positive, which meant that my derivative function lied above the x-axis. Okay, so this is actually a really interesting observation. If the original function is increasing, that means that the derivative has to lie above the x-axis because it has to be positive. For the second portion here, the graph itself was decreasing up until here, oops, which means, of course, that the derivative, being the slope of a tangent line, was negative, so my graph had to lie below the x-axis, the graph of the derivative. And then finally, the last one, same thing again, so this was increasing once again. I cannot spell, whoa, increasing. So for the graph itself, that meant that my tangent lines are of positive slope, which means that the derivative values have to lie above the x-axis. Now, we can summarize some of the key things that we're seeing on this, because this kind of analysis will be useful for a number of applications later on. Okay, so this is just a summary of important things to note, and this is a fairly comprehensive summary, I should say. These are essentially all the important things that you should note. So first of all, the derivative is 0 at local highs and lows, and on the flip side of that, if I did have any corners or cusps or jumps or asymptotes, those are the points, or those are the situations when the derivative does not exist, which means I would not have been able to sketch a tangent line at those points, which means I wouldn't be able to have computed a slope of the tangent line, and the derivative graph would also have some kind of hole or discontinuity in it. But the other two important points to note is that if the function is increasing, let's say like this, then of course if I were to draw a tangent line anywhere here, it would have a positive slope, which means that the derivative itself is positive at that point and hence lies above the x-axis. If the function is decreasing, then the situation is exactly reversed, because if I were to draw a tangent line at this point, the slope would be negative, which means the derivative value is negative, which means it lies below the x-axis. Okay? So this is how one is to produce the graphs of the derivatives from the graph of the function, just using these important things to note. So in the next example, we're going to tie in the graphical representation of a derivative and the verbal and meaningful description of what that actually represents in context. So let's just remember one of my favorite applications is because it's my favorite application for a number of reasons. It is the actual ultrasound that technicians perform on babies when they're still in uterus. The reason I find it fascinating is because I actually only found out that that's how they measure things when I was myself pregnant. This is not my daughter, this is my best friend's second child. And the reason I really like this ultrasound is because it shows exactly what is going on. So you have 2 points that the technician have picked to be points of importance, which is the top of his head and the tailbone, or some approximation of where both of those points are. Then the technician picks which measurement he or she were able to take fairly accurately, and that way the machine knows which function to actually plug that measurement into. So in this example, I'm not giving you a formula for the actual femoral length, but I'm giving you a functions graph of that formula. This function approximates the femoral length in millimeters as a function of fetus age in weeks. And we're asked to actually compute the same things but at 2 different points in time, and then maybe talk about what trend do we see in the computations that we've performed. So let's take a look first at what is it we're trying to compute. First, we're asking to approximate, so that tells us that we're going to have to use estimation from the graph. And we're asked to approximate the instantaneous rate of change of femur growth in 20 weeks. So first of all, instantaneous means we're after the derivative. And the derivative, because we don't have a function, we have to use the graph. So we have to think of a graphical representation of a derivative, and that of course is the slope of a tangent line. Now I'm given a particular point at which I would have to compute the slope, so that's 20 weeks. So let's take a look at our graph. So at 20 weeks I have a point right here. Again, this is going to be purely estimation from the actual graph. So I'm going to draw what I think looks like, that's a fairly reasonable tangent line at that point. If you're doing this together with a friend, of course, your estimations might be different because you drew a slightly different tangent line, Okay, in fact, I can probably do quite a bit better. Something like this, right? So I have to approximate the slope of this line, which means I have to pick 2 points somewhere on this line and compute rise over run. Okay, so let's say that slope of a tangent line is approximately equal, and I'm just going to pick 2 points. So in fact, I can pick the point that I sort of chose here, and then a point, let's say, somewhere here. Okay, and I have to compute rise over run between these 2 points. Again, it's an approximation, so none of my answers are going to be exact, but it should give me a pretty good idea, or like I should be in the ballpark, okay? So let's say this point was about 30, this point is about, what is it, 15, this is about 14 then, and that's 20, right? So rise over run would be 30 minus 15 over 20 minus 14. So that is 15 over 6, which is 2.5. And we have to think of units here. The femur length was in millimeters, so my y-axis is in millimeters, and the fetus age was in weeks. So my x-axis is in weeks, so this is going to be millimeters per week. So if I were to write an actual sentence as an answer, I would say that in 20 weeks, the femur length grows approximately at 2.5 millimeters per week. Okay, but that's only at 20 weeks. We notice that, of course, in the beginning, the growth was different than later, and towards the end of pregnancy, it's different still. So remember that the value of the derivative changes depending on the point which you are computing it at. Okay, so the second question is asking for the exact same thing, but at 30 weeks. So we're going to have the exact same logic here. So the instantaneous rate of change, once again, is a derivative. And once again, we only have the graph, so we have to compute the slope of the tangent line at 30 weeks. And I'm going to leave this as an exercise to you to construct what you think to be a reasonable tangent line at 30, and then pick some points along that line to be able to compute the slope of it. I'm going to discuss part 3 though, because I don't really need to see the computations to do it. It's saying, does the rate of femur growth increase or decrease with age? So it's asking, what is happening? Does it, as the pregnancy goes on, does the femur length grow faster or slower than in the beginning? Now, the rate of change is the derivative, and the derivative is the slope of a tangent line. So it's essentially asking, are the tangent lines getting steeper or shallower? And we can see here that, of course, like at the beginning of pregnancy or at the first ultrasound or something like that, this is pretty steep. So at 20 weeks, it's pretty steep still, but I can see that at 30 weeks, it's already starting to level out. Whereas by 40 weeks, which is the normal length of pregnancy, it's already fairly flat. So here we can say that it is decreasing with age. So an important thing to note here is that it's still growing. So the actual length continues to increase, but it's increasing less fast.
For a few more applications. We have seen this example of hummingbirds earlier in the course, and we have actually seen this graph as well. So here we have that the energetic gain in calories increasing with time according to this graph. Again, a sort of familiar shape. If we were to approximate this function, we would likely rely on linear hill function as our go-to model because we can witness the linear behavior near the origin and the plateau behavior towards what seems to be a horizontal asymptote. Here, however, we're asked to recall the average rate of a function and the instantaneous rate of change of a function. So over the first minute, what do we have? Notice that the time here is measured in seconds. So over the first minute means we're looking between 0 and 60 in terms of seconds. Recall that the average rate of change corresponds to a secant line or a slope. Let's be precise, slope of secant line. Which means that if I connect my 2 points, 0 and 60, with a straight line, the slope of it is precisely what the average actually represents. So the slope of this is my average rate of change. Okay, now how do we compute it? Well, we have to compute the slope of this line, so I can take the rise over run between these 2 points. The rise is going to correspond to the distance, the difference between the y values, and the run will correspond to the distance or the difference between the 2 x values. So in terms of analytical form, I can come up with a formula. Let me write down the slope of secant line is what we're computing, which is the average rate of change. And while I do not have a formula, I will actually write down the algebraic expression for this. So it's going to be the energy intake in 60 minus the energy intake at 0 divided by 60 minus 0. Now I only have a graph, so my values here are going to be approximations from the graph, but what I have is the energy at 60 will look like it's approximately equal to 1,000. The energy is 0 at 0, and then divided by 60. So overall I have 1,000 over 60, which, if you plug it into a calculator, will be approximately 16.67. And now what are our units? The units on the top here are the units of E, which are calories, and the units on the bottom here are the units of time, which is seconds. So calories per second. So as a result, we can say that on average, the hummingbird is consuming 16.67 calories per second over the first minute. However, we can of course see that this graph isn't always constant. The hummingbird is consuming quite fast in the beginning and then slows down her consumption as it runs out of the nectar to actually eat. And the next question isn't actually asking to compute the instantaneous rate at any particular point. It's specifically asking when is the instantaneous rate of change is equal to the average. So is there a point on this curve where the hummingbird is actually consuming calories at that average rate? So let's dive in and actually explore the terms here. So what I have here in terms of terms are instantaneous rate of change, and the average rate of change. So the instantaneous rate of change, remember, this also corresponds to the derivative, but in particular graphically, it's a slope of tangent line. Whereas the average rate of change, which is what we want to find this being equal to, average rate of change. I know I'm writing this over and over again, but if you take anything away from this course, it's literally these two connections between the graphical, the verbal, and the analytic expressions for these two main concepts. So average rate of change is the slope of secant line. Now the slope of the secant line we already computed, right? It's this one, 16.67, and it's this line right here. So if the slope of a tangent line, the instantaneous rate of change, is to equal to the slope of the secant line, the average rate of change, the slopes being equal means that the two lines we're looking for are parallel. So this is a very important connection. We need to find a point where the tangent line, so as a conclusion to this, find where tangent line is parallel to the secant line that we already drew, right? Because parallel means the slopes are equal. Equal slopes. So let's take a look at the picture. Here I have my secant line. I need to find a spot on this graph where when I draw the tangent line, it's going to be parallel to my secant line. So this can take a few tries, keeping in mind that this is what I want to be parallel to. And I would say it's approximately somewhere here, right? Before that, the tangent line is too steep. After that, the tangent line is too shallow. I'm looking at something like here. Now, notice that because I am sketching this by hand and I don't have a precise formula for the graph, this, of course, is simply an approximation. But this tangent line, and therefore the instantaneous rate of change, is approximately where this is going to be parallel to the average rate of change here. So I can say that this happens, so let's say the tangent line is approximately parallel to the slope secant line at this point right here. So in my approximation, it's going to be at 19. Your approximation, of course, can be slightly different. And again, because it's an approximation from the graph, as long as you're in the right ballpark, this is all good, but it has to be justifiable. So tangent line is approximately parallel to secant line at t equals 19 seconds. Okay, we can again think about what actually happens at this point though, right? We notice that the graph before that, all of the tangent lines here are going to be steeper, which means that the bird is collecting nectar faster up until this point. Here, it's collecting nectar at exactly the average rate, and afterwards, it's collecting nectar slower than the average rate. Let's take a look at one more application, the melting Arctic sea ice. We know that during the increasing temperatures on Earth in general, in particular ice, is melting at both of the poles, and this is something that ecologists have been tracking for a number of years now. This is a function that is fitted to the data. So the red points are the actual data points, and we have managed to fit this blue line approximately through it, so we can work with that as a function. First of all, we are asked to determine what are the units of this function and what they actually mean. So in terms of the function itself, the units are going to be sea ice extent in millions of square kilometers. So what does that mean for the units of the derivative? The derivative, remember, is the slope of a tangent line, which means it is rise over run, which means that we're looking at the units of y divided by the units of x in terms of purely units and not just the numbers. The units of y here are the actual units for our function. So millions of square kilometers divided by the units of x, which are years since 1980. So per year. So if we are computing the derivative, the units of it are going to be millions of square kilometers per year since 1980. Okay, so not since the dawn of time, but since this particular year, because this function is only fitted to the data since 1980. We're now asked to approximate the derivative at 20. Again, I don't have a formula yet, neither can I actually compute with a formula. We haven't talked about differentiation rules, that will come up next. So for now, all I have is a graph to rely on. The derivative on the graph is represented by a slope of a tangent line at that point. So this will be equal to the slope of tangent line at 20, not anywhere, but specifically at 20. Now, again, I am going to plop a point on 20 here and draw myself a tangent line. Your tangent line might be different than mine, and that's totally okay. As long as our approximations are somewhat similar, it's actually okay that they vary a little bit. Both are just approximations and therefore cannot be exact anyway. So this is my approximate tangent line, and now I actually have to figure out the slope of it. And here is where I will take some points on my tangent line, not on my function, but rather on my tangent line, that I can spot and see that are consistent, right? So I'm not going to say equals here. I'm going to say approximately equals, because I am really just estimating from a graph, estimate from graph. It's not an exact value, and I'm fully aware of it. So what are some points that I can take here? Well, maybe if I extend it a little bit further here, I can actually use the grid to help me out, right? So the 2 points that I can take are, for example, this point and let's say the point of the actual tangency right here, right? So what is my rise over run between these 2 points? I'm going from this point, for example, to this point. So my rise is going to be whatever this corresponds to. So let's say 7.7 minus the y coordinate of this point, which I will approximate as, let's say, 6.2. divided by the run. So however much I've actually ran between these 2 points, the difference in x values. So this point was the one I plugged in first, so its x coordinate is going to come first. 10 minus 20. I'm going to get negative 0.15. And that is in the units that we discovered in part 1. So millions of square kilometers per year. So notice that this number is negative, and we expect it to be negative because my tangent line clearly here has a negative slope. Negative units means that the function is decreasing. So that, in our interpretation, means is decreasing with time, and in particular, 20 years after 1980, so in year 2000, it's decreasing at the rate of minus 0.15 millions of square kilometers per year. Okay? In fact, watch out. If you got a positive number here, you knew you made a mistake somewhere because the tangent line is clearly negative, and therefore the slope has to be negative as well. And the last part here, is the derivative at 30 bigger or smaller than the derivative at 20? Explain. Again, I don't have a formula, neither do I know how to work with a formula yet. I can only use the graphical information to interpret the answer here. The derivative at 30 will be the slope of the tangent line at 30. In fact, let's actually write that down. So what I have here is the derivative at 30 is the slope of the tangent line at 30. And the derivative at 20 is the slope of the tangent line at 20. So the question is, which of these slopes is bigger? Well, I already have the tangent line at 20 drawn, so let me draw a tangent line at 30. Let me color code this so that it's not as confusing. There we go. If I now draw a tangent line at 30 here, I notice that even if I am doing so quite roughly, that my tangent line is going to be steeper, right? It looks like the graph is in fact decreasing faster and faster. So simply by eyeballing and estimating from the graph, I'm going to conclude that this tangent line is steeper than this one, and therefore S of 30 is going to be larger than S of 20, which means that if I do compute this number, I will get a larger negative number, indicating that in the year 2010, the ice is melting faster than it was melting in the year 2000.